Okay, so I just made up some numbers here of how many purple starchy, purple sweet, and yellow starchy kernels you might have calculated. And where these come from would be the number of purple starchy kernels, which means individuals, divided by the total number of kernels or individuals. And that gives you a number. And so that would give you 0.56. And so then I multiplied it by 10. And so what this is just basically saying is that if you had 10 kernels, 10 individuals, you'd expect 5.6 of them to be purple starchy, 1.8 to be purple sweet, 0.6 to be yellow sweet, and 2 to be yellow starchy, which is kind of weird, right, because they're fractions. But you could also think of, if you had 100 kernels, 56%, 18%, 6%, and 20%. So maybe that would make more sense to you. It doesn't matter in any case because it's the same proportions, and that's what matters. Okay, so what you want to do is to work the different characteristics individually, because purple, yellow, so the color, I guess it's the red gene, is on one chromosome, and then the SU, sugary gene, is on another. So you can work them separately. And I've marked them, the purple and the yellow, and then here's the 2 starchy, and there's the 2 sweet. So let's just look at purple and yellow. So what I'm going to do is to count up how many there are of each. So for purple, so I'm just worried about purple, yellow. How many purple do I have? Well, I have 5.6 from the purple starchy, and I have 1.8 from the purple sweet. So if I add those together, I get 7.4. Okay, so then we have yellow, and this should be the rest of them. But how many yellows? Okay, we have 0.6 from the yellow sweet, and we have 2.0 from the yellow starchy, so that gives us 2.6. And hopefully that adds up to about 10, so that'd be like 100%. So what this is saying is in our population of plants, 74% are purple and, or not plants, but our kernels, 74% are purple and 26% are yellow. So if we look at that and we try to figure out what kind of ratio that is to each other, so the kinds of ratios you're looking at in genetics problems typically are things like for a single cross, you're looking at 3-to-1, you're looking at 1-to-1. Sometimes we might see a 2-to-1 if there is a group that's dying. You might see a 1 to 2-to-1 if there are 3 phenotypes. So those are the kinds of things you're looking for with your single traits when you're looking at a cross. So if you look at that, which one is this closest to? Well, you'll notice here that this is almost 75%, 25%, if you want to think of it that way. So it's almost a 3-to-1 ratio. So maybe it's easiest if you do it by, percentages, I don't know. But in any case, it's 7.4 and 2.6 is about a 3-to-1 ratio. So what does that tell you? That tells you that for you'd want a 3 purple to 1 yellow. And in order to make that cross happen, so purples we said were both these genotypes, and yellow was that one. So you might just already know what gives you a 3-to-1 ratio. That would be good to know what kind of cross does that. But if you didn't, you'd want to say, okay, you want 1 yellow, and then all the rest of the boxes you want to have a purple. And you know that you have to trace it. Like this has to go back here to the parent, and that has to go to this parent. So this one would also be a possibility in this box. And where did you get the big R? Well, you need a big R here. And then you need one here in order to have this offspring. So then it gives you this. So then you look and say, what are the parents that I just crossed to make a 3-to-1? That's a monohybrid cross, so 2 heterozygotes. Yeah, so that tells you that this is the cross for the yellow purple part. Okay, and then we do the same thing for the starchy sweet. So how many starchy do we have? Well, we have 5.6 from the starchy purple ones, and we also have 2 from the starchy yellow ones. So that's 7.6. We have from the purple and sweet 1.8. From the yellow and the sweet we have 0.6. So that gives us 24. So when we're looking at our possible ratios, 3-to-1, 1-to-1, maybe a 2-to-1, or 1 to 2-to-1, we only even have 2 phenotype, so it can't be that. Again, you're going to see it's about 75%, 25% or so, and so that's about a 3-to-1 ratio there. And so, again, it's the same, it must be the same thing to get us the 3-to-1 ratio. So that means it's the same thing. In this case, it's the same thing twice. It doesn't have to be the same ratio twice, but in this case, and again, so that's a monohybrid cross. So this would be for your S's, and so it's the same deal here. You need, for every 3 starchies, you need 1 sweet. So here's a sweet, and that means that each parent must have had a little s, and then that means that these boxes are like this. And then we know we have to have some starchy, so we have to have 3 boxes of starchy, which is good. Oh, and in order to have this box be starchy, this parent also has to have a starchy allele. And so then you have, again, a monohybrid cross. So those are the parents. So then you just put it all together. And then you say, okay, so one parent needs to have a big R, little r, meaning that it's heterozygous for the purple. And then the second allele, it's also heterozygous for starchy. So you have a purple starchy parent plant, and in fact, this case, you have another purple starchy parent plant, and those are the 2 parents that you expect to make offspring like this, which is basically a 9 to 3 to 3 to 1 ratio, but 9 to 3 to 3 to 1. Now, it's not going to be those numbers on here because these are percentages, so that would be like 9 out of 16, which is something like 56%, I'm not sure. But in any case, all that matters is that you can work it backwards and see which kind of combinations. So if you had something like that was giving you, like we looked at in class, just put this way off to the side, some of these numbers who were like a 5.0 and 1 or something like, or 0.9 and 4.90, something like that. So where we saw that there were almost 1-to-1 ratio, right? You can see those are almost the same. So basically this is saying, 50% to 49%. So that would be a 1-to-1 ratio of those characteristics. I think this was purple to yellow. Okay, so we know the yellow is the 2 and the purple it can be either one of these. But in order to get a 1-to-1 ratio, basically what you're looking for here is for every 1 yellow, you get 1 purple. So what's the second allele here? Well, you treat this back to these parents. Each one had to give a little r. Where did this big R come from? Well, it must have come from this parent, right? And so then this individual must be heterozygous there, so it can't be that. It has to be this and this. So that's just telling you that those are the offspring. So it's a 1-to-1 ratio. So then basically, like we just did what the parents are. So how do you get to be a 1-to-1? You have a parent that's heterozygous, and then we only have one option here, but the parent must have 2 alleles. So that just means that you have a parent that's homozygous recessive. So a 1-to-1 ratio is classic test cross. So if you get a 1-to-1, you know that it's these are the parents, a homozygous recessive, and a heterozygote would be the parents. And if you got other combinations, you can get a lot of different combinations. I mean, I gave them some of you. So let's say you got a 2-to-1 ratio, which is kind of different. So you either have to have 2 options or 4 options. There's no like 3 options for genotypes unless one is dead. And so that must be what's happening with this scenario here. So what this is telling me is that you have one, let's just do it like this, recessive, and then you have 2 of the dominant phenotype. I mean, then you have to have another box here, so we'll just see what happens with this. So because you have a double recessive, both parents must have to have a recessive allele. And then you want two that have a dominant phenotype. So where does that big R come from? Here's one parent there. This must be like that. This. So then the question is here, what do we put with this other parent? Well, if we put, so if you put a little r as an option, then you can see what babies that would happen. So if this would be a test cross again. So you see you're not getting your 2 to 1. In this case, you're getting a 1 to 1 ratio. Now that's not what we want. So that can't be right. So what's our other option? Maybe it's a heterozygote parent. So that would give you here. Now this is giving you a 1, this would give you a 3 to 1 ratio. Now if these are all the same phenotype, so this is all like purple in our case, and that's yellow, 3 to 1. So you're like, okay, though that's still not a 2 to 1. When you get a 2 to 1, it's telling you that probably one of the phenotypes has a problem and is dead, or doesn't make it to development. So for example, here, if your big R combo caused the offspring to die before it was developed, so you never even got those kernels to develop, then all of a sudden you're left with 1 and then 2. So 2 to 1 ratio of purple to yellow kernels. So that would be, this is a little more complicated, unusual situation. But in that case, what you would say is that, well, you see a 2 to 1 ratio for the purple to yellow. So what that's making you think is that you have 2 heterozygous parents, but RR is dead. Meaning that the offspring that were to be RR never make it, so you never see them in the ratios. So there's your parents, but RR is dead, so that's why you get the 2 to 1. Let's say you got that, and then you did your starchy sweet, and you added up your numbers, and it turned out to be a 1 to 1 ratio that you saw. Well, now you know that means it's a test cross. So if it's a test cross, that means a homozygous recessive, and darn, with the S's. Okay, homozygous recessive cross with a heterozygote. So then what would you do? Then you just say that you have a parent that is purple and starchy, so that's this and this, and a parent that is purple and sweet, that's this and this, but you'd also have to note RR babies die. I don't have to say it quite like that, but RR phenotype doesn't develop, and so that's why you get the funny 1 to 2 ratio, the kind of unexpected. So basically you just do the R's by themselves, the S's by themselves, and then put the 2 parts together. Yeah. So hopefully it's not as bad as you thought it was.